Okay, so, and the last part of this lecture is the fabrication of yarns via in situ CVD. So again, these carbon nanotubes are made by CVD. And in this case, the basically directly right out of the CVD, carbon nanotubes are extracted. So in the previous methods, they were extracted not in the shape of a yarn. In this method, they're extracted on a motor that winds them up into carbon nanotube yarns. Typically, there are two motions with these here. One is a rolling to collect carbon nanotubes. And then there is another one, which is typically twisting in this way. So if I want to show you the angles, the borders, the vectors of the twist, one is this way, one is this vector, so it twists them into yarns, and then there is another one which this vector, which collects the yarns. And so these are examples of that. And so, I mean, like they did some investigations. For instance, they realized that, and by the way, the person who invented this method is Alan Windle. He's a professor in University of Cambridge. And so a few interesting points is the higher they were winding them, basically the higher this velocity here. The linear density was going down. Basically, they were getting thinner fibers. And linear density means mass per unit length. But fibers were more compact. The specific density was higher. So basically, in thicker fibers, there's less chance for carbon nanotubes to get combined to each other. Now, the other thing that is kind of very, very interesting is, for instance, the specific strength, which is this graph that I'm showing you here, this one, this bottom one. So for instance, at very high winding rates, they ended up reporting a strength of about 2 gigapascal per specific gravity. These are specific strength values, okay? So this is GPa per SG means GPa per gram per cubic centimeter. Because SG means a specific gravity that's measured with respect to water, and the density of water is 1. So a specific stress or a strength is stress divided by density. So at very high winding rates, where the fibers were the tiniest, they were the ones that had very low linear density, like this case. So basically this case, that corresponds to this graph here. They measured the strength on average of about 2 gigapascal. What is very interesting here, which, I mean, it's a paper in Nature, it's very good paper, but look at the high uncertainty. One thing about this paper was that they did many, many experiments. And so there's a high uncertainty in the strength they reported. Now, this is one of the nicest experiments I've seen. I think that was one of the reasons this work was published in Science. They realized, okay, they had this high variation in the strength, and they were like, why? Okay, it's a fair question. So two things they noted. One was they measured strength. So basically, they had a carbon nanotube yarn. They were loading it like that and like this. And they used different gauge length. So this is the gauge length, okay? They used different gauge length, and here's a very nice result about what they reported. So look at this. For the case of 20 millimeters, the strength is distributed, has a normal distribution, and most of it, the peak of the measurement, is below 1 gigapascal per specific gravity. When they go to 2 millimeters, something very interesting happens. A second peak appears here. And when they go to 1 millimeter, another peak appears here. I'm sorry, the same peak, but becomes much, much stronger here. And this higher peak is, look at how strong this higher peak is. So basically, this higher peak corresponds to about 7 GPa per specific gravity. So basically, for instance, since the specific gravity of carbon nanotubes is about 2 gram per cubic centimeter, it means at 1 millimeter gauge length, they could measure a strength of 7 times 2, basically gigapascal. And so basically, let me write it here. So sigma over rho was about 7 for this peak, and it was GPa per SG. And in addition, the SG of carbon nanotube is roughly about 2. So then the strength they could report for that is 14 gigapascal. This is a very high strength, and it's really deserves some attention. But one thing that can become clear, especially when you compare this case with this, that this peak appears here, but then at 1 millimeter, there's another peak appearing here. That means that with this experiment, what they mean is that there are certain defects in the material that reduce the strength. But the fact that I see a much higher strength at 1 millimeter gauge length here means those defects on average are more than 1 millimeter apart from each other, so that when I take a 1 millimeter gauge length, there's a chance that I don't see those defects. So basically, imagine this is my carbon nanotube yarn, and I have some defects here, 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 and these defects on average are more than 1 millimeter apart. So on some of the samples that I cut, I don't see those defects. So like this would be my one sample. This could be my other sample. And then there could be a sample that I cut that I see this defect. This guy, for which I see the defect, so this is the gauge length, will give me this peak. These guys will give me this peak. But these guys, the strength that I measure here is going to be absent here, because anytime I take a gauge length of 20, means from here to here, I will have at least one of those critical defects in my structure. Okay, and so the other thing is, they also notice that the strength and the stiffness kind of scaled together, which means there are certain defects that affect the strength, not modulus. For instance, if you have just a single void in your material, it more affects the strength than modulus. But if you have distributed voids all over your sample, or distributed short overlap length all over your sample, then strength and modulus will scale together. Because when you're increasing material when you're taking material out of everywhere in your sample, then modulus will drop. But the strength, which is a local phenomenon, like the weakest link that I explained, that will also go down. So basically, these are flaws that do not induce significant stress concentration, because if they did, they would have reduced strength much more than elastic modulus. So there were follow-up studies on this that they noticed some certain defects in their material that was happening with the periodicity of about 1 millimeter on average. And there were follow-up works too, which were aimed at eliminating those defects. And I want to finish these set of slides with this work from the same group. So now, going back here once more, this point, this data point, deserves attention because it's really high. It's the highest strength. How did they manage to get this 14 gigapascal of a strength? That's a very important question. And in order to answer that, they looked at their SEM images. You remember I told you that if you have two carbon nanotubes that are like one here and the other one here, the strength will not go up very much after certain points when you increase overlap length, the plateau in the strength. I hope you remember that. But in all those studies, the width of the junction, if it was high, or the strength of the junction, the total force that the junction would take, would scale with oh my God, okay. So the force would scale with the width of the junction. So in a typical carbon nanotube, we're talking about these two. And so the overlap is somehow something like this. But if I can flatten these out, I can go to this versus that. Now my overlap length is much higher. And so what does that require? A lot of it, when you have very large carbon nanotubes, they can collapse and they can get this shape. Because when they become this shape, then the van der Waals interactions between this surface and this surface will lower the energy of the system. However, if you have if you have a multi-wall, if you have a multi-wall carbon nanotube, then the buckling, the collapse into this structure will become energetically unfavorable because bending these guys will be energetically unfavorable. So for a single wall nanotube that have large diameter, or few wall carbon nanotubes like here, these are few wall carbon nanotubes that are very large. They can buckle, they can laterally buckle, and they become basically, they form this shape. But if you have many layers, many shells, then in order for the outer one to buckle, the inner one has to buckle first. And the inner one buckling requires a lot of energy, makes that buckling energetically unstable. I'm going to stop here, and thank you.